Hi, this is Xuxiao Li, research engineer from Global Engineering and Materials, along with Dr. Matsu Ilan Chilian, postdoc from Purdue University. We will be presenting a multiphysics coupling of resin infusion and fabrics deformation using customized STAR-CCM and Abaqus on behalf of the primary presenter, Dr. Jim Luo. We would like to thank the support of our co-authors, Ryan Enos and Dianyun Zhang from Purdue University. This work is funded by an SBIR program under the sponsorship of Air Force Research Laboratory. So here is an overview of our process modeling of liquid composite molding. So we have two components of our models. In the infusion model, we use the commercial software STAR-CCM to simulate the flow in dual scale porosity. So that's the intra-tow infusion and the intra-tow infusion. On the curing model, we use the Abaqus heat transfer analysis to obtain the temperature and degree of cure. And then we use Abaqus stress analysis to obtain the residual stress and distortion. The cure-dependent material constitutive law is used for the pure resin, incorporating micromechanics and laminate homogenization approach. Finally, we demonstrate a framework of coupling StarCCM and Abaqus by simulating a flow-compaction coupling problem in vacuum-assisted resin transfer molding. So in STAR-CCM flow simulation, we solve the Navier-Stokes equation, which essentially reduced to Darcy's law in the liquid composite molding. The volume of fluid method is used to capture the flow front. We first carried out a benchmark experiment for the purpose of model validation. It is an L-shaped beam structure using the vacuum-assisted resin transfer molding. Resin is ejected from the upper left corner and vent out from the lower right corner. After infusion, the resin is cured at 350 Fahrenheit for 2 hours. An exemplary simulation result is shown here and compared with the benchmark experiment. The pressure distribution is shown, and the white line indicates the flow front. We can see that the flow front pattern as well as the filling time can match with the experiment. So to capture the dual-scale porosity, we'll adopt the mass sink approach to model the absorption of the resin into the tows. A mass sink term is added in the continuity equation, which is a function of tow saturation degree and pressure. With the mass sink, we can simulate the partially saturated tows behind the flow front, as shown by the tow saturation on the left video. We see that the white line is the flow front, and behind the flow front, the tow saturation is below 1. We also see from the right figure that once the intra-tow porosity is fully saturated, which is the blue curve, we still need a bleeding time for the intra-tow porosity to be filled, so that the overall saturation, which is the red curve, becomes 1. To calculate the mass sink term more accurately, we take a mesoscale approach where we estimate the yarn dimension from our fabric and generate a texture model for the representative volume element, or RVE. Then we import the RVE geometry into STAR-CCM to do the meshing and for the intra-tow infusion simulation. Here on the left of the red surfaces is the flow front in the intra-tow infusion. On the right, we show the pressure distribution on the slice of the RVE. The pressure gradient is established from the tow surface into the air, driving the impregnation of the resin into the tows. So we can run multiple mesoscale RVE simulations and calculate how fast the tows can absorb the resin. So we build a digital library for the sink term as a function of pressure and tow saturation. In our macro-scale infusion model, we can use this digital library to calculate the sink term and update the pressure and tow saturation. So next, I will transition to Matsu to talk about the deformation model in curing.
As we mentioned in the summary, the first step of the curing model is to conduct a heat transfer analysis, which determines the temperature and cure history inside the composite based on the cure cycle and internal heat generated due to the cross-linking of the resin when the heat is applied. The second step is where the stress analysis is carried out, obtaining the resulting stress and deformation response based on the temperature and curing history. In the heat transfer analysis, the resin-specific heat and thermal conductivity and henceforth the relaxation modulus are dependent on the degree of cure, time, and temperature. O'Brien et al. Developed the relaxation modulus for E.862W resin system as shown in the equation above, and we are able to obtain the relaxation modulus from the modulus at reference temperature using temperature shift factor. For the thermoset resin, the curing process can be divided into three regions as shown. Dilation occurs at a defined point in the curing reaction, after which the resin is able to carry loads. Before this point, the resin is in the liquid phase and stress accumulation is negligible. After gelation, the resin transitions to the solid phase and the thermal and chemical strain should be considered in the constitutive relations. When the curing temperature is above the resin glass transition temperature, the resin is at a rubbery state and it is assumed that the resin modulus is close to 0 and its Poisson ratio is close to 0.5, since a gel can be approximated as an incompressible material. Based on this, the constitutive law is simplified and stress is calculated. A mesoscale model is developed to determine the effective laminate RVE thermo-chemomechanical properties based on the laminar properties. For the laminate composite, the unidirectional properties are transformed to the RVE coordinates based on the orientation of each ply. Then the stacked plies are homogenized by an extended classical laminated plate theory based approach to obtain the full 3D properties. Finally, we use a Python script to obtain the spring-in based on the residual stress and deformation from the curing model. Here we see the spring-in response of the L-beam as time increases during the curing cycle. The spring-in gradually increases and reaches maximum during curing. The results obtained from our curing model are in close comparison with the experimental results.
We have established the framework for the STAR-CCM and Abaqus to communicate with each other. Shown here is an example of using this framework to solve the flow-compaction coupling in vacuum-assisted resin transfer molding. So in the STAR-CCM, we simulate the infusion of a flat panel, so a pressure gradient is established. In the separate Abaqus model, we simulate the compaction by the atmospheric pressure on the panel. So for each time step, we extract the resin pressure from STAR-CCM and interpolate that in Abaqus. The resin pressure balances part of the atmospheric pressure, so the compaction is alleviated and the volumetric strain is changed. And using that strain, we update the permeability in STAR-CCM and the process repeats. An exemplary result is shown here, where the color contour is the strain along the thickness direction. We see that the panel is under a compressive state indicated by the negative strain. As the resin is infused, the compaction is alleviated, the compressive strain is decreased, and we see the thickness of the panel is increased. Here we show the pressure distribution, the fiber volume fraction, as well as the permeability. We see that the pressure is decreased from the left gate to the right vent, and as the resin pressure will increase the panel thickness, the fiber volume fraction is decreased as the resin is infused into preform. Finally, the smaller fiber volume fraction leads to larger permeability, which speeds up the infusion. In summary, we use STAR-CCM and Abaqus to model the infusion flow and residual stress in the liquid composite molding process. A coupling framework is demonstrated by a flow-compaction coupling example. Future work includes passing the infusion modeling results as the initial condition for the curing model. For example, the compaction-induced deformation as well as the pre-gelation degree of curing. Thank you for your attention.